Welcome back to ECE 441A, 541A. Several announcements. Maybe the main one is you do have your first exam, and that's going to be a week from Friday. Hopefully you know that. There is study material on D2L for that. There's a lab that is due after the exam, but the material that's covered in the lab is probably important. It is important for exam number 1. And there's videos and notes on D2L that you can watch and fill out. And there is a sign-up sheet, if we can figure it out, for lab number 1 being passed around. But it has rows of, it has 45 rows, and on each row should be the team members. Each block or each cell in the form is going to be your last name and first name. Hopefully that will be, and you can form your own teams of up to 2 to 3 for lab number 1. I'll try to find out what the room number is. That's why there's a question mark. But Josie will point you to the hardware. It's in one of the rooms on the 3rd floor of ECE. And you should be able to sign up in the stock room for a lab time, and the lab shouldn't take you that long if you watch the video and do the pre-lab. I've had students go in thinking they can just do it cold, and they break the equipment, they waste a lot of time. So I would recommend, strongly recommend, that you watch the video, understand, do the pre-lab, then it's a fairly quick lab time that you can go in and do the steps. It's very cookbook in nature in terms of the lab, but I'm wanting you to get a feel for a hardware aspect of this class. That's lab number 1. Today what I want to do is start with a linearization quiz, and then we'll talk about linearization. With that said, I want you to look at these 4 equations, 4 sets of equations, and tell me yes or no on your own. Take 1 minute to determine whether these 4 equations are linear or nonlinear. Go. So you can just write down A, B, C, and D, yes, no, whatever your decision is on that. You're not turning this in, but I do want you to do it. Maybe I will just eyeball and do a visual compliance on who's doing it and who is not doing it.
You call it Matthew and then Thursday and something like this messing up here.
All right. Now, is system A linear or nonlinear? System B, linear or nonlinear? Why is it not linear? Because I have 2 sets of coupled equations? No, that doesn't matter. It's this term, isn't it? It's the cross product of x and y. That forms a nonlinearity. C, linear or nonlinear? How many think it's linear? Raise of hands. How many think it's nonlinear? Why is it nonlinear? So we have a nonlinear function, sine of x. Actually, it's sine of the velocity of x, sine of x prime. That makes it nonlinear. 4, linear or nonlinear? How many think it's linear? Show of hands. How many think it's nonlinear? Show of hands. Why is it nonlinear? So in this case, that's actually just a coefficient that's time varying. It's not a nonlinear operation on any of your state variables or inputs. It's not a cross product term. So in fact, this particular system has time varying coefficients, but it's linear. We probably won't be dealing with time varying coefficients in this class, but that does not constitute a nonlinearity in system D. Now, what we want to do is learn a little bit more about linearization, or the linearization process. And I'm going to simply scroll through a few lines just to give you a feel for this, and then we'll slow down and start working through this process. But a linear system, which is like our x prime equal f, satisfies superposition, an additivity property. If you have two arguments that are added, then that should be the same as taking the function of each individual argument and adding that result. And it should have a homogeneity property, meaning if you scale the argument, that's the same as scaling the output of the function of that argument. So additivity and homogeneity make a linear system. You probably already have this mental image of something that's linear. A function is linear if you can evaluate it at x naught. If you know the function, you can find f of x naught. If you select an argument x sub 1, then you know what f of x sub 1 is. What we are doing is we're applying that same idea to a system. So we have dynamics involved. That's the left-hand side. That's the time rate of change of our state vector, x prime, where x can be a vector. I'm giving you an example of just a two-dimensional vector, or a vector x that has two coordinates, but we have an A matrix that in general could be time varying and still remain linear, meaning all of these entries could be functions of time, but they can't be functions of any of the variables themselves, the state variables or inputs, other than through coefficients. Meaning, if you look at that system and brute force multiply out and generate the right-hand sides, you see that each of those right-hand sides, there's no product terms, there's no x1 times x2, and there's no terms involving a nonlinearity. It's simply a constant scaling, a sum of the state variables and the inputs. What are some common nonlinearities? We have saturation of an amplifier, or you could think of a resistor that's no longer following this V is equal to Ri characteristic. Maybe it starts varying from that linear relationship at the extremes. That's another nonlinearity. A dead zone, meaning maybe nothing happens for a while and then we start moving relative to the variable x, and we could have backlash. where the relationship between x and f of x is obviously dependent on where you are relative to the particular condition of the system. And you could think of meshing gears, meaning it may take you a while to start that movement, and then once you maybe want to change directions, maybe you stay stationary until you mesh again to go the opposite way, and that's what this sort of four-sided figure represents, our meshing gears that now allow for you not to be able to sort of backtrack on the same path that you started. We want to perform analysis and design in this class, and if we started with nonlinear systems and wanted to live in that domain, we would have a hard time getting very far in this course. Meaning, there's a lot to learn, a lot of insight can be gained by looking simply at linear systems, and a lot of systems we can accurately model and well enough by looking at their linear properties, or looking at them as a linear system. So we want to do some analysis and some design on linear systems, and how do we do that if we have nonlinearity in our system? Then we could do a piecewise analysis, or what we are just going to generically call linearization. We are going to linearize the nonlinearities that might exist in the system. Let's look at what that means. And a lot of times it's helpful to just work through an example. Suppose we have a system, x prime of t minus 2 x squared of t is equal to u of t. We typically solve for the highest power of the derivative and put everything else on the right, and everything else on the right is this function f of x and u. If we start to put this equation into that form, then we have 2x squared of t plus u of t that's now a nonlinear f of x and u. And where is the particular nonlinearity in this case? It's coming about because of that squaring operation, or this product of x times itself. There is our particular nonlinearity. And we want this to be linearized, but right now it's sitting in front of us in the form of this function f being a nonlinear expression in terms of the x's and the u's. It could have had an x times a u. It could have had a sine of u. There's a lot of different ways it could have been nonlinear. Here I'm just illustrating it with one example by saying, let's just look at a system that's 2x squared plus u. And what was commented on before was, can we just sort of do a piecewise linearization, or look at a piecewise, if we had an expression or a function f of x that's illustrated here by this blue curve, then if we're interested in how the system is behaving near or close to a position, let's say, of x naught, then what we're after is, can we now express this or model this blue wave type expression more like a linear function itself. And now we would be interested in looking at this function f near or operating around f of x naught. That's the image that we need to sort of keep in mind when we're performing or looking at this linearization process. Have you ever looked at approximating a system or a function in some kind of using some technique before? Or expanding, here I'm giving you more hints, expanding a function around a particular point, and now Taylor comes to mind, right? Our friend Taylor, actually the Taylor series. That's what we're going to use to try to linearize these nonlinear expressions. Meaning, if we have a generic nonlinear expression, f of xu, a right-hand side that is governing our dynamics of the system, the time rate of change is influenced by f of xu, then if we do a Taylor series expansion around a nominal location in its operating regime, let's say that's described by x naught u naught, then we have what it is right there, and then these small variations around that point. And we can find that then by taking the partial of f with respect to x, evaluating that partial. Everywhere we see an x, we replace it with x naught, and x could be a vector. So we could have an x1 naught, an x2 naught, an x3 naught. On the exam, maybe sixth order. So you might have 6 and maybe 4 inputs. So you might have a u sub 1, 0, a u sub 2, 0, a u sub 3, 0, a u sub 4, 0. Does anybody have any lozenge? I have a... So we're evaluating that partial fraction at those locations, x naught and u naught. I was teasing on that lozenge. Thank you, though. X minus x naught. But that's not the end of it, is it? We just keep going. We have many, many more terms. We can do then the partial of f with respect to u, the input. Again, we evaluate that. And we then multiply it by the difference in our input u and its nominal value or location, and we keep going. In our Taylor series, we would have the second partial of f with respect to x, partial of f with respect to x, and then the partial of f with respect to u, etc. We have these higher order terms, but if we stay close to this guy, and if the variation x minus x naught and u minus u naught is not very large, then we're going to neglect those higher order terms because they will be scaled or multiplied by x minus x naught squared and x minus x naught cubed. And those just get smaller and smaller as long as x minus x naught and u minus u naught are small to begin with. We're assuming then that these first two terms in this expansion dominate the approximation of f of x around that f of x naught u naught. Question? No. So the question is x naught meaning time 0? X naught is some position. So let's say that or it's some position of your state variable. It could be a velocity, it could be an acceleration, it could be a voltage. It's just some nominal value that, think of a pendulum swinging What might be an equilibrium condition? It might be vertically down. So we might linearize that nonlinear behavior around its vertically down location. And in that case, maybe theta is 0. Theta naught, the x naught might be 0. If it was vertically up, if it was a pendulum that's vertically up, which could represent a rocket, now maybe we want that angle theta to be pi, and our x naught would be pi. But it's just a location where these are the nominal values around which up here we are moving. Meaning this is just some location in the entire trajectory, but we want to force our behavior to be right around that location x naught. So that could be at 1 meter, or it could be at, maybe we're cruising along and we're at 70 miles per hour. That's our x naught. So hopefully that will become a little bit more clear as we move forward. Now, if we can rewrite this, it will become crystal clear. We can rewrite that by putting this f of x naught u naught on the other side, so that we now have f of x u minus f of x naught u naught. And since we are throwing away the higher order terms, now we have an approximation of partial of f with respect to x evaluated at x equal x naught, u equal u naught, times x minus x naught, plus partial of f with respect to u, again evaluated at x equal x naught, u equal u naught, and that's u minus u naught. Where this left side is really this variation around a nominal operating condition. Another visual that I like to have people think about is, suppose you have a satellite orbiting a planet. That satellite might have a nominal path around that planet. That's the x naught u naught. And if somebody or somehow that gets bumped away from that nominal, that's giving us then this variation f of x naught minus f of x naught u naught. And we want to know, how does the system behave relative to a small variation around x naught u naught. Let's go back to our example. Sometimes it helps just to do it mechanically, do the math, and then try to back out the understanding. Here we go. We have x prime of t is equal to 2x squared of t plus u of t. A nominal operating point for this particular system could be x not equal to 1 and u not equal to minus 2. Where did that come from? We want that nominal operating point to satisfy that governing differential equation. That's our nominal operating trajectory, or our nominal equilibrium point, or our nominal operating condition. So we want to see, is it true that if we differentiate x naught, that's equal to the right-hand side evaluated at x naught u naught. That's the nominal state around which we want to model the dynamic behavior. What happens if I differentiate 1 with respect to x? That's 0, isn't it? There's no x there. What happens if I now evaluate 2x squared plus u naught at the nominal operating condition? So I'm saying 2x squared of t plus u of t evaluated at x equal x naught, which was 1, and u equal u naught, which was minus 2. I have 2 times 1 squared plus a minus 2. Giving me 0. So I have the 0 on the left. I end up with 0 on the right, so it's consistent. That's actually a nominal. What I can conclude then is I can say, therefore, x naught and u naught indeed satisfy the governing differential equation. And before we get too much further, let me establish some notation. The notation will be x minus x naught. I'm going to call delta x. Again, this could be a vector. You could have different components in delta x. It could be 3 tall if it was such a system. We have u minus u naught is equal to the small variation in my input, which I will call delta u. That means that anywhere I see an x, I could just as easily say, well, that's x naught plus delta x. Or if I had the input u, I could say that that's u naught plus delta u. Let's now use this notation in our particular Taylor series formulation. In that we had an x prime, but that's now x naught plus delta x differentiated, which says that that's x naught prime plus delta x prime. So that's the time rate of change of our nominal state of the system, x naught prime, plus the time rate of change of the small variation around x naught. That's the left-hand side, but that's equivalent, or that's approximately f of x naught u naught plus the partial of f with respect to x, again evaluated at that operating condition, times x minus x naught, which is what we said we will label delta x, plus partial of f with respect to u, again evaluated at the nominal operating condition delta u. Now, and this is a result of our Taylor series. And if x naught is where we nominally operate, then the time rate of change of x naught is indeed equal to f of x naught u naught. If x naught satisfies our underlying differential equation, then these two terms are in fact equal, and they're on opposite sides of this equality, so essentially they cancel each other out. X naught prime, by definition, satisfies f of x naught u naught. These two now go away, and what are we left with? On the left-hand side, which is sitting over here now, that's the left-hand side, we're left with that piece, which is the time rate of change of x, delta x, and that's now approximately equal to the partial of f with respect to x evaluated at the operating condition times delta x plus the partial of f with respect to u delta u. Let's go back to the future. Let's go back to the example. Put this in play. Actually perform some of this. This is what we want to use. We want to now apply or utilize that expression. The time rate of change of this small variation around the nominal operating condition is equal to these partials, which will just give us constants when we evaluated x naught and u naught, times delta x plus some constant times delta u. And hopefully you see that this is our normal linear expression. This is x prime equal ax plus bu, where the a is this matrix of partial derivatives. The b is the matrix of partial of f with respect to u. I promised we would go back. So let's go back to the example. And here, f of xu was 2x squared plus u. And this is why you took your calculus, either in middle school, high school, or maybe even in the university. Right? But you had your calculus. So, what's the partial of f with respect to x? This is a very challenging derivative or differentiation. That's just 4x, isn't it? And now if I evaluate that at the nominal values for x and u, which are x naught and u, what was x naught in our example that solved the nonlinear differential equation? That was 1. And what was u naught? That's minus 2. If we now replace all the x's and all the u's with 1 and minus 2, what do we end up with for that partial of f with respect to x? That becomes a difficult 4. What about the other piece? That gives us the first piece, partial of f with respect to x. What about partial of f with respect to u? What's the partial of f with respect to u? What happens when we evaluate that? At the nominal condition? It's still 1, isn't it? So now what do we end up with? Now we actually end up with a set of linearized dynamics for that original nonlinear system. Here's our linearized dynamics. We have delta x prime is equal to partial of f with respect to x evaluated at x naught u naught, and what did we just calculate that to be? Partial of f with respect to x, that was 4, times delta x This in parentheses was just our partial of f with respect to x evaluated at x equal x naught equal u naught, plus what was the partial of f with respect to u evaluated at those nominal values. That was 1 times delta u. And if we didn't like those deltas floating around, which really just means small change around x and u, we could relabel this and say, oh, our system that we are now wanting to play with, let's just replace delta x with z. So now we have z prime is equal to 4z plus, let's say, some input v. And now we have a linear system to play with or to think about. Is that system stable? What we're saying now is if we linearize this nonlinear system around that operating point of x not equal 1 and u not equal minus 2, if somebody perturbed that system away from that nominal point, will it return to that nominal point? Will it be stable, or will it leave if we don't do anything about it, if we don't implement any kind of control? Where do we need to live in the complex S-plane if we want a system to be stable? If we were looking at, so here's the S-plane, here's the imaginary axis, here's the real axis, and we wanted a system to be stable, where would we want the poles of that system to live? Whoops. We want to be over here, don't we? We want the real parts of those poles. If we had two poles, let's say they were complex and they were right here and here, then we want those poles of our system to be in the left half plane. They have negative real parts for stability. And I know that you're going to be texting this a lot, so let's just abbreviate that LHP for the left half plane. Anytime now we start talking about stability, then we want poles in the LHP, the left half plane. Now let's go back to our example. And see, is this particular system stable or unstable? This is in the time domain, isn't it? This expression, this differential equation. Where are our poles? What domain are they? If we start talking about poles, what domain are we living in? We're in the S domain, which isn't the time domain, it's the frequency domain. So we need to convert this into the frequency domain. In other words, we can Laplace transform that governing equation. And if we're only interested in the dynamic behavior of the system, not the solution, then we can neglect all the initial conditions in this transformation. What happens when we Laplace transform a derivative? That's just s times z of s. What happens when we Laplace transform z that's scaled by 4? And v is just plus capital V of s. We want a transfer function. We maybe want our output to be z and our input to be v. Let's collect all of the terms that scale z on one side. And now we have our transfer function g of s is the ratio of the output over the input, which becomes 1 over s minus 4. And if we start talking about poles, those are the values of s that cause the denominator to vanish. What value of s causes the denominator to vanish? And if you look at that, if you had to plot that as an x, as a pole in the complex s-plane, where would that be plotted? In the right half plane, in the RHP. It's okay. That's why we're taking this class, so we can stabilize unstable systems. But we have to understand, what are we living with? This is now in the right half plane. Which means if we didn't do anything to that system and somebody kicked it off from its nominal operating point, it would just continue to move away from that operating point. It wouldn't return if we didn't put any kind of control around that system. We can see that in terms of this system behavior if we look at the impulse response. Of that system, which is really just the inverse Laplace transform of the transfer function. The impulse response is, what if you hit this system with an impulse? What's the Laplace transform of an impulse? Laplace transform of delta. You could go through and look at the integral definition of the Laplace transform. The delta does a, to start doing. I'm baking, I'm sifting, remember? It's that sifting operation of the impulse. It now evaluates the argument at 0, t equals 0, and you see that the Laplace transform of an impulse is 1. So if we wanted the output, y of t, due to an impulse, and the Laplace transform of the impulse is 1, then we're really just looking at the inverse Laplace transform of the transfer function. If we now look at the inverse Laplace transform of g, capital G of s, what happens to that when you put it into the time domain? E to the 4t. What happens to that when time gets big? Time grows. It just goes crazy, doesn't it? It goes unbounded. This is another way of understanding that in fact our system is unstable. And what we want to do in this class is, if we had this G of s sitting here, this was our original system, we've maybe linearized and we want to control it around that nominal location. We may want to introduce our own dynamics, d of s, in the form of a controller to allow this system to no longer misbehave and go unstable, but maybe to be a little bit more favorable to what we are wanting to do in terms of control that system around the operating point. And that's what we want to learn how to do, but first we have to figure out how do we create all of these G of S's. You've already spent a lot of time with 4 different representations: state space, block diagram, transfer function, and differential equations, which is what we started with today. And then we had a nonlinear differential equation today. We've then linearized it, found a G of S, and now we can start to control that linear system, capital G of S. So that now we wanted to extend this. Our original X example was first order. We simply had one pole in this G of S, didn't we? What if we wanted to look at a higher order system? Suppose X is now a vector, and we want to perform the linearization. And I had already hinted that maybe you might have a 6th order or 6-dimensional state on your exam. X1, X2, X3, X4, X5. You can do that on the exam. Today we'll just do 2. How's that? So what's this? This is a 2nd order case. For now. That means if I look at x prime equal to f of xu, what does that look like in a 2-dimensional or in a 2nd order case? I now have an x1 prime and an x2 prime on the left, and what do I have on the right? I have an f, but now it's a function of x1, x2, and let's just say that we have a scalar or single input, and we have an f of x1, x2, and u, but those are not necessarily the same x, so let's label those in the rows that they hold in that vector for x1 prime, x2 prime. x1 prime is now f1, and x2 prime is f2. We've already done one row, except we didn't have this coupling behavior. Now we have to worry about the coupling. That's the left-hand side, which is now x1 naught prime, x2 naught prime, plus delta x1 prime, delta x sub 2 prime, which is approximately equal to f of 1 of x1 naught, x2 naught, u naught, f sub 2, x1 naught, x2 naught, u naught, plus. And now what do I have? Now I have a matrix of partials. I have the partial of f1 with respect to x1. I have the partial of f1 with respect to x2, partial of f2 with respect to x1, partial of f2 with respect to x2. What do I do with all those partials? I evaluate those at x1 equal to x1 naught, x2 equal to x2 naught, and u equal to u naught. And that gets multiplied by delta x1, delta x2. That's my x minus x naught in vector form. Plus one more piece. I have partial of f1 with respect to u, partial of f sub 2 with respect to u. Again, evaluating at the nominal values for x1, x2, and u, and scaling that by the vector delta u. We're done. Now you can do a sixth order piece of cake. And we'll pick up at that point on Wednesday, but this will be on the exam, so you will want to make sure that you do start to get a feel for how to do the mechanics of this linearization process.